Welcome to the first lesson video of Chapter 6. Today we're going to be learning about Section 6.1, Roots in Radical Expressions. Our objective is that we can find nth roots. Let's begin by discussing how for every power we have a corresponding root. Here's a couple examples. 5 squared is equal to 25. When you take the square root of 25, you get 5. 5 cubed is equal to 125. When you take the cube root of 125, you get 5. 5 to the fourth is equal to 625. When you take the fourth root of 625, you get 5. And 5 to the fifth power is equal to 3,125. And when you take the fifth root of 3,125, you get 5. So you can see in each of these examples that when you square a number and when you take the square root, you're doing the inverse operation. This leads us to a definition of what the nth root is. So, for instance, if we have a to the n is equal to b, where a and b are real numbers and n is a positive integer, then a is known as the nth root of b. So n represents a positive integer, so whatever positive integer we are raising that base to. Now, there's two different cases. Let's talk about the first case, and that is when the exponent n is an odd number. So if n is an odd number, then there is one real nth root of b, and that is denoted in radical form as the nth root of b, as shown right here. Here's an example. I have my n as 3, which is an odd number. If we take the cube root of 27, we get 3. That does not include negative 3. We only get positive 3. And you can always check your answer by taking your answer, 3, raising it to whatever the n value was, 3 to the third, and that equals 27. So that ensures that the cube root of 27 is equal to positive 3. Here's the other case. If n is an even number, for example, over here at right, we have the square root of 100. And for square roots, we typically don't write the number in front, the n value, but I'm just going to put the 2 there just to show you that it is an even root. If we take the square root of 100, we can get positive or negative 10. And that's because we can raise positive 10 to the second power and we get 100, or we can raise negative 10 to the second power and we still get positive 100. And that works because when we raise a negative number to an even power, the negative sign cancels out. So if n is an even number and the number under the radical is positive, then we are going to get 2 real nth roots of b. In this example, I got positive 10 and negative 10, which are both real answers or real numbers. The positive root is called the principal root or the principal nth root, and it's indicated by the symbol the nth root of b. And the negative root is its opposite because we have the negative nth root of b. The other possibility is when we have a negative number under the radical and the nth root that we're still taking is an even number. If this is the case, then we will not be able to get any real nth roots of this number. And that's because when you take an nth root of a negative number, you will actually get an imaginary solution, which is not a real solution. So take a look right here. We learned this in previous chapters. If we took the square root of negative 100, our answers would be positive or negative 10i, because when we take the root of a negative number, an even root, we're going to have to bring in the imaginary number I. And we're not actually going into that right now. So in this case, we would not get any real roots of that number under the radical. And if we were taking any nth root of 0, such that n is a positive integer, our answer is going to be 0. So now let's make a little bit more sense of all this and do a couple examples together. Before we begin example 1, let's talk about a couple key terms that will be helpful in doing these examples. The n value, the number in front of that radical, is called the index, and the index gives you the degree of the root. The sign is called the radical sign, as you already know, and the number under the radical is called the radicand. In example 1, part A, we're going to find the real cube roots of the numbers 0.008, negative 1,000, and 1/27. So the first question I have for you is, how many real cube roots are there going to be? Well, the cube root is the same thing as a third root, and that means the n, or the index, is an odd number, which is 3. So that means there is only going to be one real cube root of each number. Remember that the cube root is the inverse operation of raising a number to the third power, or cubing that number. So what we're trying to do in each of these examples is think to ourselves, what number do we have to multiply by itself a total of 3 times to get the answer in the end, or the number that we're starting with? So let's go to our calculators. I want to show you the button that we're going to use for cube roots. Go to Math, and then down to number 4. That's the cube root. And then now let's type in 0.008. We find out that the answer is 0.2. So that means the cube root of 0.008 is 0.2. And we're going to check our answer by just raising that number to the third power. And we get the original number of 0.008. Now let's do the same thing, except this time we're starting with a negative 1,000. We find out that the cube root of negative 1,000 is negative 10. Now let's take negative 10 and raise it to the third power. And we get negative 1,000, so that checks our answer. Now let's take the cube root of a fraction 1 over 27. And we get 0.33 repeating. You can go to Math. Hopefully you just know this fraction by heart, but go to Math and then Fraction, and we find out that the cube root of 1/27 is 1/3. And 1/3 to the third power is this decimal, and then let's go back to fraction here, and that is 1/27. So that ensures that we did the right thing. In part B, we're asked to find the real fourth roots of the numbers 1, negative 0.0001, and 16 over 81. So let's start the fourth root of positive 1. Remember, we talked about this a little bit earlier, that when we're taking the even root of a number, we should be able to get a positive and negative root. So the fourth root of 1 is actually plus or minus 1. And you always want to include the plus or minus symbol when you're taking an even root. Now let's check our answer. If we raise positive 1 to the fourth, we just get positive 1 for our answer. If we raise negative 1 to the fourth, we also get positive 1. And that's because when you multiply a negative number an even number of times, that negative sign cancels out. Since negative 0.001 is a negative number, we are not able to take the fourth root of this number and get a real answer, or a real root. And that's because when you take an even root of a negative number, that brings in the whole imaginary unit that we talked about earlier. And we're just focusing on real roots right now. So that means because we have a negative number here, there are no real fourth roots of this negative number. And I want to show you real quick on the calculator that this calculator confirms this solution. So if you were to take the fourth root of negative 0.001, I want to show you real quick how to do that. Go to, actually, you have to start with 4, and then go to Math, and then down to number 5. So you can see it has an X in front, so that basically stands for the nth root. So when you're using this, you always want to type in the index first. So we're taking the fourth root of negative 0.001, and we press enter, we get non-real answer. So that confirms that we're not able to get a real answer for this part. Now we just need to take the fourth root of the fraction 16 over 81. So what we're really doing is just taking the fourth root at the top of the fraction, the fourth root at the bottom of the fraction. So the fourth root of 16 is 2, because 2 to the fourth is equal to 16. And the fourth root of 81 is 3, because 3 to the fourth is equal to 81. So that means the fourth root of 16 over 81 is equal to positive or negative 2/3. And that's because when we raise 2/3 to the fourth power, we get 16 over 81. And when we take negative 2/3 and raise it to the fourth power, we still get positive 16 over 81. So when we're taking an even root of a positive number, we should get a positive and negative root. or solution for our answer. According to the fundamental theorem of algebra that we learned in Chapter 5, a polynomial, for example, x to the fourth minus 1 equals 0, has 4 roots because the biggest exponent, or degree, is 4. Only 2 of these solutions, or roots, are real. In this chapter, we are only going to focus on real roots. So in example 2, we are asked to find each real number root. Part A gives us the cube root of negative 8. So what we want to do is find a number whose cube is the radicand, or the number under the radical, which is negative 8. So what number do we need to raise to the third power to give us negative 8? Well, when we raise negative 2 to the third power, we get negative 8 for our answer. So that means the cube root of negative 8 is equal to negative 2. In part B, we are given the square root of 0.04. Remember, whenever we're given a root and we are not told what the index is, or the number in front of that radical, we assume that it is a square root. So if it helps you to put a little 2 there, you can, and otherwise you don't really need to put the 2 there. So what number do we need to raise to the second power to give us 0.04? When we take 0.2 and raise it to the second, or multiply that number by itself, we get 0.04. So that means the square root of 0.04 is equal to 0.2. Now you may be thinking, why aren't we including negative 0.2? Well, that's because in the original square root we did not have a plus or minus in front. So the square root of 0.04 represents the positive square root. In part C, we're asked to find the real number root of the fourth root of negative 1. So we're thinking to ourselves, what number do we raise to the fourth power to give us negative 1? For this problem, there is actually no real root because there is no real number that we could raise to the fourth power to give us an answer of negative 1. Remember, when we're raising a number, whether it's positive or negative, if we're raising that number to an even power, then we're going to get a positive answer out. So there's no real root for the fourth root of negative 1. In part D, we're asked to find the square root of the quantity negative 2 squared. Now, at first glance, we think, oh, this might be very similar to part C, but actually you need to reduce the negative 2 squared, or simplify that. When we do that, we get positive 4, and we know that's a perfect square. So the square root of 4 is equal to 2. And we can check by squaring 2. When we square 2, we just get positive 4. And again, we're not including the negative solution because we don't have a plus or minus in front of that original square root. Part D actually leads us to the take note box shown below. And this generalizes the idea of the nth roots of nth powers. So if we have any real number a, the number is under the radical a. If we're taking the nth root of a to the n power, then we can have 2 different possibilities for our answers. We can get a if the index is an odd number, so whatever number we're raising to that odd number and we're taking the nth root of that, we just get the whatever number is the a value. But if the n, or the index, is an even number, then we only get the absolute value of a. So we're not getting a negative number, and that's because when we take an even root, we're just going to get a positive number out. These absolute value bars ensure that the root is non-negative. Non-negative means either 0 or a positive number for your solution. Remember, you must include the absolute value when n is an even number, so when you're taking the even root. And you must omit it or not include the absolute value when the n, or the index, is an odd number. For each of the following radical expressions, we need to put it in a simpler form. So in part A, we're given the square root of 16x to the 8th. Since we are simplifying a square root, we want to use properties of exponents to write the entire radicand, or expression under the radical, as a perfect square. So I'm going to rewrite this radical as the square root of 4 squared times x to the 4th raised to the 2nd. And that's because 4 squared is equal to 16, and x to the 4th raised to the 2nd power, or squared, is equal to x to the 8th. Because remember, when we're raising a power to another power, we're just multiplying those exponents. So now I can combine, since 4 and x to the 4th are being both raised to the exponent 2, or being squared, I can just rewrite this as the quantity 4x to the 4th raised to the 2nd, or squared. And when I take the square root of that quantity squared, remember those are inverse operations, so I just get the expression 4x to the 4th. And we do want to include absolute value symbols because we are taking an even root. And the absolute value of 4x to the fourth is equal to 4x to the fourth. Remember, absolute value just keeps things non-negative, so we don't have to worry about the negative sign for our answer. So that means the square root of the original expression 16x to the eighth is equal to 4x to the fourth. We don't have to have absolute value symbols in our final answer because 4 is already positive and x to the fourth is always non-negative. When we raise a number to an even power, we will get a positive number out. In part B, we are asked to find the cube root of a to the sixth, b to the ninth. So what we want to do is write the entire radicand, the expression under the radical, as a perfect cube. So I know that I can raise a squared to the third to give me a to the sixth. So I'm going to write this as the cube root of a squared raised to the third, because when I multiply 2 and 3, I get the original exponent of 6. And I can rewrite b to the ninth as b to the third raised to the third, because when I multiply 3 and 3, I get 9, which is the original exponent. Now, because I am cubing each of those expressions, a squared and b to the third, I can write that as one quantity. So the cube root of a squared b cubed, all raised to the third, or cubed again. And since I'm taking the cube root of the quantity a squared b cubed all cubed, that is undoing each other, so I just get the expression inside the parentheses. So I get a squared b cubed. Since the index was an odd number, 3 in this case, we are not going to include absolute value symbols here. In part C, we need to find the fourth root of the expression x to the eighth, y to the 12th. So what we want to do is write an expression to the fourth power. So let's rewrite this as the fourth root of x squared raised to the fourth times y to the third raised to the fourth. So let's just make sure we did that right. So 2 times 4 is 8, which was the original exponent for the x variable, and 3 times 4 is 12, which was the original exponent for the y variable. So now, because we have both expressions raised to the fourth, we can combine them into one expression. So I have x squared y cubed raised to the fourth. And because that outside exponent and the index 4, those are the same number, we just get the expression that is inside the parentheses. So we get x squared y to the third. Now the question is, where should we put the absolute value symbols? Well, we definitely need to include absolute value symbols because we started off with an even root. In this case, we're going to start with the absolute value symbols around the whole expression, but then we're going to simplify a little bit. We don't need the absolute value symbols around x squared because when you raise a number to an even power, you just naturally get a non-negative answer. So we really just need the absolute value symbols around the y to the third. And that's because we want to ensure that we're getting a non-negative answer for our entire expression. If we didn't have those absolute value symbols there, we wouldn't be able to ensure that the root is positive when y to the third is negative. In example 4, we're given the opportunity to apply our knowledge of radical expressions. So here it is. Some teachers adjust test scores when a test is difficult. One teacher's formula for adjusting scores is a equals 10 times the square root of r, where a is the adjusted score and r is the raw score or original score. If the raw scores on one test range from 36 to 90, what is the range of the adjusted scores? So we need to adjust the lowest raw score and the highest raw score. So given that r is equal to 36, we can find the adjusted score by just plugging in 36 for the r. So we have the expression 10 times the square root of 36. Well, we know that 36 is just a perfect square, so that means we're really just multiplying 10 times 6, because 6 is the square root of 36, and that means the adjusted score would be 60. So given a raw score of 36, the adjusted score would be 60. Similarly, we're going to be using the formula to find out the adjusted score for the raw score of 90. So 10 times the square root of 90. Well, 90 is not a perfect square, so we're going to use our calculator to figure out the approximate decimal. So let's do the square root of 90. We find out that it's approximately 9.487. When multiplying 10 by that number, we get the number 94.87, and rounding that a little bit, we get approximately 95. Since we're given the lowest and highest scores of the original test, that means the other scores must be between those. So that means the adjusted scores range from 60 to 95. So the lowest score is 60 and the highest score is 95 with the adjusted formula. That completes lesson 6.1. Make sure you write down these 6 lesson check problems, work through them, and let me know if you have any questions the next time we meet.